earlier in class, we came and we chose a random f of x function. On that function, we chose a random point, a, f of a. We came and we drew the tangent line at that point. We said that if we pick a point, x, relatively close to a, then the tangent line can be used to approximate the f of x value. That was the whole idea of talking about using the tangent line as a linear approximation of f of x. And that's what it is, a linear approximation. F of x is still the actual value, but the line, the tangent line, can be used as a way to approximate f of x. And sometimes there are some functions that are very difficult to work with. So therefore, a linear approximation can really make all the difference. So then, in this case, if we choose a random x, then we know that f of x will be approximated by f of a plus f prime of a times x minus a. And if you remember, the tangent line here, it is usually called L of x. And L is there to remind us of linearization or linear approximation. This is saying the same thing, that f of x can be approximated by its linearization or its tangent line. So right there. I also want you to notice that in an equivalent way, if I subtract f of a from both sides, I end up getting that f of x minus f of a is approximately equal to f prime of a times x minus a. And this difference right here, f of x minus f of a is just a change in f. Or in other words, if we go back to this graph, for example, giving x, this is going to be f of x right here. So then delta f is precisely this vertical difference right here. This difference is delta f. And you're going to see that in example 1 and example 2, we're going to be trying to approximate the difference in the y values. Sometimes you're going to be using your linearization to approximate f of x, but sometimes you're going to use it to approximate delta f. In other words, f of x minus f of a. But you know that in order to approximate delta f, you can do that by using the product of f prime of a times x minus a. I'm going to do a further improvement here on this formula. I will say that f of x minus f of a is approximately equal to f prime of a, but instead of saying x minus a, I'm just going to say delta x. And I want you to remember that delta x is just a change in x values as we go from a to x. This is all there is to that. But this is the way that the formula appears in most calculus textbooks. Going back to the graph, when you pick your point A, right here, this is your point A, you go horizontally to the y-axis to find f of a. When we came and we chose x, let me go up to my graph over here, then you go horizontally across to look at f of x. We also very nicely that this is the vertical change. This is exactly the actual vertical change in y values. Whenever we use the approximation, the vertical approximation is going to go from this point on the tangent line to the height of f of a right here. So it's going to be this vertical change here. This corresponds precisely to f prime of a times delta x. So then again, if you notice, this vertical change right here, this tiny one from the tangent line down to the level of f of a is the approximate vertical change. But whenever you go all the way up to the graph over here, from the graph to the level of f of a, this is the actual vertical difference. So then, the error that is involved in the approximation is this distance right here that I'm shading in yellow. This is precisely the error involved. And what you always want to be able to do is to minimize this gap right here, this yellow gap. The smaller the yellow gap is, the better the approximation is going to be. So, for example, then, what you want to do is to be able to choose an x value that is even closer to a. If you notice, the closer I get to a, to the point of tangency, the smaller that tiny error is going to be. So that goes hand in hand with the entire idea that the tangent line is the best approximation for f of x if and only if x stays relatively close to a. Now, ladies, what I want us to go and do here is to go back to notation, a few technicalities that I want to talk about. For example, the author, you may have seen, uses what he calls differential notation. Differential notation. This is simply just dx versus dy. Simply speaking, this says that dx pretty much replaces delta x. In other words, if instead of using delta x, you want to use dx, you can go ahead and do that. They mean exactly the same thing. dy will refer to f prime of a times delta x. Well, you know what? Instead of saying delta x, I'm going to use my new differential notation. So dy is exactly equal to that product. And now I can rewrite this expression here, f of x minus f of a approximately equal to f prime of a times delta x. I can replace delta x with dx. F of x minus f of a will be represented by delta f. The delta there will stay. We don't use a differential for f. Delta f, we can say, will now be approximately equal to dy, because if you remember, dy refers to this product right here. But you're going to see that in this entire section, my preferred notation will remain being the one with delta. I will still write that delta f is approximately equal to f prime of a times delta x. Even though I know that I can replace delta x with dx, I can replace this entire product with df, with dy, I still prefer to write down the product itself. It keeps reminding me that the approximation involves f prime of a times delta x. But that will be your choice, whatever makes you feel comfortable. In question number 1, they're giving us a function. F of x is equal to the square root of 1 plus x. They're giving us an initial point, at least the x value, which is a equals to 8. And they're telling us that we're going to move away a little bit from 8 by 1 unit to the right. So delta x is equal to 1. That means that we're looking at an x value, at a change in x value from 8 to 9. That's going to correspond in a change in y values. And it's exactly that change in y value that we're trying to approximate. But we're not going to go ahead and calculate the actual change. Even though we have a function, we're not going to do that. We're going to go ahead and approximate that change using the linear approximation technique that we just learned. For example, I know that within that approximation, I'm going to need that derivative. So I'm going to differentiate right now so that I can get that out of the way. If f of x is equal to the square root of 1 plus x, that is the same thing as writing 1 plus x to the 1/2. That means that f prime of x is going to be equal to 1/2 1 plus x to the negative 1/2 times 1. So then that will be 1 over 2 square root of 1 plus x. I will also need the value of the derivative at 8, so I will take care of that right now. F prime of 8 equals to 1 divided by 2 square root of 1 plus 8. That means 1 over 2 square root of 9, therefore 1/6. Now that I have all of that, I can do the approximation. Remember, the actual change is really given to me by f of 9 minus f of 8. Even though I have a function, I am not going to plug this into the function and do my subtraction. I'm going to use the linear approximation. We already know that delta f is approximately equal to f prime of 8. Instead of putting values, let me just say a for now is equal to f prime of a times delta x. That really means that this is equal to f prime of 8 times 1. 1 is delta x. So now substituting, f prime of 8 we know is 1/6 times 1, we easily get 1/6. So all of a sudden, let me continue here, delta f, the change in f, is approximately equal to 1 divided by 6. So this is the approximation. Remember, if you want to get the actual difference in y values, you can always go ahead and calculate this difference right here. But the whole point is to be efficient and to use derivative to do that approximation. Now the question is asking us to compute the error that is involved here in the approximation. We already said that the error is equal to the absolute value of the actual change in f minus the linear approximation. The actual change is equal to f of 9 minus f of 8. I'm going to put that difference in brackets, minus the approximation, which is 1/6. All right, the actual change, I'm going to have to calculate it here. There's no way out. If I want to calculate the error, I need to know what is the actual change. That will be square root of 10, and I'm plugging these x values, 9 and 8, into the original function. The square root of 10 minus the square root of 9 minus 1/6. This will be, whenever you use your calculator and you do these computations, you're going to end up getting absolute value of negative 0.004389. And by having it within absolute value, that means that the error involved will be this decimal. That seems like a very small error. So it gives us the impression that the approximation of 1/6 is a pretty close approximation.
Can we type?
In question 2, they're asking us to estimate this difference right here using a linear approximation. And again, we are approximating a difference. So you can think of the difference in the y values of 2 points of a function. What I'm thinking here is for the function f of x to be expressed by x to the 1/4. Or in other words, the fourth root of x. When I look at the actual values that they're giving us right here, 16.5 versus 16, that makes me feel that we should consider a to be equal to 16. First of all, because this is the smallest value that we have, and then 16.5 is just a change of 0.5. So imagine delta x to be equal to 0.5. So our starting point will be at 16. Delta x is going to be equal to 0.5. Now, because we're going to be using a linear approximation, we need a derivative. That means that f prime of x will be equal to 1/4 x to the negative 3/4, which is going to be equal to 1 over 4 x to the 3/4. You can re-express it in radical form as the fourth root of x, all of this to the third. We will also need to calculate f prime of 16. I'm going to go ahead and do that. And another way to know that you have the perfect value for a being 16 is because this is a value whose fourth root you can easily calculate. You don't even need a calculator for that. You're going to have then continuing 1 over 4, fourth root of 16 to the third, which is going to be equal to 1 over 4. The fourth root of 16 is 2, and 2 to the third, that's going to give us 8. That means 1 over 32. That becomes f prime of 16. Now that we have that, we are ready to approximate the change in the y values. You can imagine then that delta f is precisely 16.5 to the 1/4 minus 16 to the 1/4. This will be approximated by f prime of 16 times the change in x, and the change in x is equal to 0.5. If you remember, just using variables, this becomes f prime of a times delta x. So then, that's going to be equal to 1 divided by 32. We already calculated that, and I will express 0.5 as 1/2. So that's going to give us 1 divided by 64. Therefore, conclusion, we're going to say that 16.5 to the 1/4 minus 16 to the 1/4 is approximately equal to 1 over 64. If you want to calculate the error involved, or even the percentage error, then you know that that's an easy calculation. In question number 3, they're giving us this decimal and they're asking us to approximate it. I will assume that I don't have any fancy calculator that can work with exponent of 1/3, or another way of saying it, finding cube roots. I will assume that I have the simplest calculator ever, those old-fashioned ones that go back to basic, the ones that are under $1 in a dollar store, for example, where you can only do basic arithmetic operations like addition, subtraction, multiplication, and division. By looking at the number, I feel that I can already consider a function f of x to be the cube root of x. Also, if you look at the actual decimal right here, 27.03, we can imagine that the starting value of x, so in other words, a, will be equal to 27. And that if we find the tangent line whose point of tangency is at 27, then we can use that tangent line, which here is called the linearization of the function. We can use that linearization to be able to approximate the cube root of 27.03. We know that f of x can be approximated by L of x. And we know that L of x is equal to f of a plus f prime of a times x minus a. So what I want right now is to find this equation of the tangent line, this linearization. I'm going to put some effort in finding that linear function, and then I am going to use the linear function to do the approximation of the cube root of 27.03. I'm going to use a line to do that approximation. All right. In order to do that, just by looking at the equation here, I need various things. I need f of a. I'm going to do that here. F of a, that's going to be f of 27, cube root of 27, which is equal to 3. I will also need to differentiate. So f prime of x will be equal to 1/3 x to the 1/3 minus 1, so negative 2/3. That's going to give us 1 divided by 3 cube root of x squared. So then, f prime of 27 will be equal to 1 divided by 3 cube root of 27 squared. And simplifying, that will be the cube root of 27 is 3. 3 squared is 9. That will give us 1 over 27. So that's going to be f prime of 27. Okay, so right here. All right. With that in mind, I think that we have everything that we need to do our approximation. But before we do that, I will continue now building the line. So L of x will be equal to f of a, in other words, f of 27. F of 27 is equal to 3 plus f prime of 27, 1 over 27, times x minus 27. And then I'm going to go ahead, distribute my values. So L of x will be equal to 3 plus 1 over 27x minus 1. That's going to give me 2 plus 1 over 27x. And that becomes the linearization, or in other words, the equation of the tangent line. Now then, I'm going to go ahead and find L of 27.03. And this is a calculation that I can do with my very simple calculator. I don't need anything fancy. I just need something that allows me to divide, multiply, and add. So then, when I do this, this is going to be equal to 3.0011111. I'm going to go to, there are how many decimal places here? 5, 6, 7 decimal places. You'll see why, because I want to calculate the error later on, so that's going to give us more accurate information. What is this telling us now then? This is telling us that 27.03 to the 1/3 is approximately equal to 3.0011111. Okay, so that's my approximation. Let's say that now I am curious about the error, the percentage error involved in this calculation. I want to know, is this a good estimate, or is my linearization just too far away from the graph? So all that I have to do to answer that question is to calculate the percentage error. We already know that the percentage error will be equal to the actual value of the function at 27.03 minus the estimate given by the linearization, so L of 27.03. That will be divided by the actual value, F of 27.03. Close absolute values times 100%. Now, to calculate the actual value right here, I'm going to have to use a fancy calculator, something a little bit nicer, and I'm going to have to calculate the cube root of 27.03. When I do those calculations, I'm going to get 3.001107 minus 3.001111. This is the estimate divided by the actual value, 3.00111107. All that times 100%. When you do those calculations, being very careful with your keys, you're going to have 0.000013%. My goodness, this is such a small percentage error. This is telling us that this approximation right here, this approximation is a very close approximation to the actual value of the function at 27.03. So you can really trust this approximation. Question number 4 is such a nice question. It really shows you the power of linearization, how you can actually get very, very close to the value of sine of 46 degrees by just using a linear approximation, basically. We should all see that the function in question should equal sine x. Also, we should remember that f of x is approximated by its linearization, and the linearization is just a tangent line, which is equal to f of a plus f prime of a times x minus a. And what I want right now is to find this linear function, because I can use this line to figure out what is going to be the sine of 46. But I'm going to do that through a linear approximation. Now, because we have to find the derivative of f, you remember that since we define derivatives of trigonometric functions, we always assume that theta is in radians, never in degrees. That means that we're going to have to go ahead and change all degrees to radian measure. But that's super easy. For example, I know that 46 degrees can be changed into radians by taking 46 degrees and multiplying by pi over 180 degrees. This will give me 23 pi divided by 90 radians. Also, we noticed that I need an a value. We haven't declared that yet. You want to be able to choose an a whose sign you know without needing to use a calculator. So then if I think of 46, 46 is close to a special angle, and that special angle happens to be 45 degrees. So I am going to let A be 45 degrees, and in radians, this is just pi over 4 radians. So there are my two values. Now I know that I need to do a few other separate calculations. I need to know what is f of pi over 4, because a is pi over 4. That means that this is the sine of pi over 4. And hopefully you remember, and if not, you can use right triangles. This is equal to 1 over root 2. Similarly, f prime of pi over 4. This is going to be equal to cosine of pi over 4, which is equal to 1 over root 2. And if you're wondering where I got the cosine, remember that f of x is equal to sine x. That really means that f prime of x is equal to cosine of x. That's where the cosine came from. All right. With all that in mind, I think that we are ready to create L of x. L of x is going to be equal to f of pi over 4, 1 over the square root of 2, plus f prime of pi over 4, so 1 over the square root of 2, times x minus a, and a is simply pi over 4. Now in my next step, I'm going to go ahead and do my distribution. So then that means that we're going to have 1 over the square root of 2, which is plus 1 over the square root of 2 of x, minus pi over 4 square root of 2. And just doing a little bit of rearranging, we're going to have 1 over the square root of 2x. Then I'm going to somehow shift all the constants towards the end so that they're there together. So I'm thinking of this as my constant term. And this becomes L of x. Okay, so let me go ahead and circle that. So this is L of x, the linearization of the function at pi over 4. Now that I have that, I'm going to use my linear function to do my approximation. 46 degrees, remember we're going to use radians, so I'm not going to say 46 degrees. I'm going to say L of 23 pi over 90. That's going to be equal to 1 over the square root of 2 times 23 pi divided by 90 plus 1 over the square root of 2 minus pi over 4 square root of 2. And then using a simple calculator, I take my time and I do those computations. That's going to be about 0.5677017 in case you want to go ahead and try it out yourself. This value should be pretty accurate. You're going to get something like this, and then when you add, you're going to get 0.7194448. Therefore, this is telling us that the sine of 46 degrees is approximately equal to this decimal that we got through the linear approximation. And then again, if you want to convince yourself of the error that is involved here, do the formula for the error. If you remember, the percentage error, the formula is the same as in as in example number 2, I think that we did together, becomes the absolute value of the actual value, so sine of 46 degrees. I'm going to use here again radians. So 23 pi over 90 minus the linear approximation, so L of 23 pi over 90, you already have that decimal there, divided by the actual value, 23 pi over 90, times 100%. And you're going to see that the percentage error is very, very small. So this number right here is a very close approximation of the sine of 46 degrees. Question number 5, the last one, is more of an application type of question. We want to be able to see how do we put some of these techniques into a more realistic use. So 5 says, let's read it together here. Newton's law of gravitation shows that if a person weighs W pounds on the surface of the earth, that's on the surface of the earth, then his or her weight, that's big W, at distance x from the center of the earth is given by this relationship. If we look at that diagram right here on the surface of the earth, the weight of the person is little w. But as soon as the person starts moving away from the surface of the earth, W here, big W, becomes the weight of the person. I also want you to notice that little w in r is the radius of the earth. This is a constant right here. Let me point that out by writing it down. This right here is a constant. So we notice that since the variable happens to be right here in the denominator, this is really saying that as x, the distance away from the surface of the earth increases, the weight of the person goes down, which makes perfect sense. If we look at part A, they're asking us to show that the weight loss at altitude h miles above the surface of the earth is approximately equal to this expression right here. What they're really saying is, imagine that we move away from the surface of the earth h amount, so h miles. What will be the change in weight loss? Well, we know that delta W will be approximately equal, and keep in mind I'm using linear approximation, will be approximately equal to W prime of A times delta X. Now, in this case, we haven't really defined A. I'm thinking of A as being exactly the radius of the Earth, so at the Earth's surface. A is going to be 3,960. And then delta X, we know, is going to be equal to H. That was practically given to us. So now with that in mind, I know that I'm going to have to find a derivative here. So W of X is going to be equal to W R squared times X to the negative 2. So I'm bringing the denominator upwards by changing the exponent to a negative exponent. And now I can use power rule to find that derivative. That will be equal to negative 2 W R squared times X to the negative 3, or in other words, negative 2W R squared divided by X to the third. That becomes the derivative. So then, if I have this, I should be able to now find delta W. Delta W will be approximated by W prime of A times delta X. Well, in this case, W prime of A will be W prime of 3960 times H. W prime, we have the expression for that. That will be negative 2 little w times the radius 3960 squared divided by 3960 to the third times h. And if I now simplify, this factor here will simplify with this exponent, so that's going to go to 1. And then everything will be re-expressed as negative 2 WH divided by 3960. And whenever you divide out the numerical coefficients, that's how you're going to get negative 0.0005 W times H. And that becomes the change in weight loss. All right, all this was part A. Now it's time to go ahead and tackle part B. That should be considerably easier. In part B, they're telling us to estimate the weight loss by a 200-pound football player flying in a jet at an altitude of 7 miles. Practically then, they're giving us little w. This is his weight on Earth. So that's going to be 200 pounds. And because he's flying, the distance away from the surface of the Earth is going to be 7 miles. We're going to go back to what we derived in part A. We know that the change in W, in his weight at that particular altitude, is going to be equal to negative 0.0005 times W, his weight on Earth, times the altitude, 7. When you work that out, you should get negative 0.7 pounds as the weight loss.